Good morning, John Gilkison here. This is Friday, December 20th, 2019, and I'm wanting to do this video on brake-specific fuel consumption as it relates to electric vehicles. So I've got the house to myself. I'm fur babysitting, so I want to see if I can't get this in. Now, I've written a blog on this, and it's on our Facebook page, Electric Vehicle Organization, SNM, which stands for Southern New Mexico. And I've been hashing this out for the last few days. The concern came up because it seems like the world is still looking at electric vehicles through fossil-fueled glasses. And people will test out trucks and they know how many miles per gallon they get, and you test an electric vehicle and it's how many watt hours per mile, and it creates a bit of confusion. And it occurred to me that you should just convert internal combustion engine powered vehicles, just convert all the power to watt hours, and then you can compare apples to apples. And so when you look at the brake-specific fuel consumption, that's rated in pounds of fuel per horsepower hour. And that has to do with the efficiency of the power plant. It's the, as I've defined it here, the efficiency of the engine, parentheses motor, calculated by the energy consumed divided by the power produced. And that's at the output shafts. I think the best way to do it is at the output shaft that turns the wheel, and not at the flywheel or anything, because you still have further losses through the transmission, and then the axles and so forth, and through the diff. And so it's disingenuous to state it any other way. What we want to know is the amount of energy that goes into the engine and the amount of energy that comes out turning the actual wheel that propels the vehicle forward. So that's the way I do it. And so what we're doing is converting pounds of gasoline into watt hours. 1 gallon of gasoline does equal 32,770 watt hours. Now this is E10 or gasoline, which most people in the United States buy. People don't, I don't know why the EPA doesn't use it as its figure, because the figure that the EPA uses is for gasoline and nobody uses anymore. So it just doesn't make any sense, although it is a standard metric. But, so anyway, and more specifically, there's 6.138 pounds in a gallon of gas. So for an internal combustion engine, for example, we have to take this 32,777 and divide it by 6.138, and that gives us 5,340 watt hours per pound of gasoline. And at that point, the BSFC of a typical gas engine might be rated at 0.45 pounds of fuel per horsepower hour. And so you have to use that as your multiplier, and you end up with 2,403 watt hours per horsepower hour. And that's not good. The definition of a horsepower hour, by the way, and I didn't put it on this board, is 746 watt hours. So as you can see, it's wasting a lot of fuel energy to get that horsepower hour. And so for an EV, for example, we're using the BSFC, and I questioned that. I didn't put it on here either, but it could be, we might want to change BSFC to read BSEC for brake-specific energy consumption, or BSPC, brake specific power consumption. I'm kind of leaning towards energy myself. But anyway, for an EV, we're going to assume 0.155, which is a good rated EV, like a Tesla, which has about a 90% efficiency of converting the energy in the batteries into motive force at the wheels. And that would give us, again, the same thing by converting the gallons figure back down. This is our standard right here for a pound of fuel. It's 5,340 watt hours. Times the brake specific, we end up with 828 watt hours per horsepower hour. And you can see the vast difference here, 823 versus 2,403. It's definitely about 3 times in this instance. So, and three times, 3x is a good working figure for electric vehicles. They're generally 3 to 4 times more energy efficient than an internal combustion engine. And I'll get into that in a minute, because you may wonder why we came out slightly less than 3 here. But assuming a 20% thermal efficiency for internal combustion engine, this leads to a problem. We can only define the BSFC for an internal combustion engine under certain conditions. And these are not conditions that you meet when you're driving. You'd have to be in a certain temperature, barometric pressure, and you'd have to be on flat ground, and you'd have to be in a certain gear during a certain speed, and so forth. And the BSFC for an internal combustion engine is all over the map. And that's one of the reasons they have to have a transmission. And there's, by the use of a transmission and other things, start, stop, fuel injection, all the accoutrements that they've slapped on gas engines, is to wring more efficiency out of them, to lower the BSFC. And that's why we're at 10-speed transmissions in vehicles now. That's why we have fuel injection and computer controls. We're doing the best I can, but there's certain limits because of the Rube Goldberg nature of the internal combustion engine. It's a heat engine, and it's got a couple thousand moving parts, and pistons going up and down, which in and of itself, by its very nature, is a problem. So, but for an EV, we can use 90% efficiency as a good working figure, which is why I pinned the BSEC at 0.155. Now the reason for this is, you remember my definition before, that a horsepower hour is 746 watt hours. And you literally cannot go below unity. In other words, if I had a lower BSFC figure in this, I could go below 746, which 746 is ideal. And so it's disingenuous to do it. Now there's reasons you may get to below that figure, and I'm going to discuss that in a second. But this is my working assumption. And that brings me out, in this instance over here, to 828 watt hours per horsepower hour. And then when you assume the 90% efficiency, you still come out just slightly above 746. So there you are. It's but when you assume the 20% efficiency here, man, you end up at 480 watt hours per mile. It's just it's ridiculous. It's just not happening. And but the reason that EVs can go below unity is because of regenerative braking. And so that's conditional, and that's outside the parameters of what we're talking about. For example, I drive my EV to the east side of town, which has a higher elevation than the west side of town. So then if I have a bunch of errands to run and I'm headed to the west side of town, I'm going downhill, and I'm recuperating energy all the time I'm going to the other side of town. So I'm way below unity. But that is not the way you would state this problem. You have to make a certain set of assumptions, and then the rest is icing on the cake. Regenerative braking, start-stop. We can get start-stop in internal combustion engines, but it's a natural feature of EVs, and so forth. So the reason I wanted to get into this is because I've seen a lot of videos on people comparing towing ability of trucks with gas engines versus Tesla Model X's, which is a ridiculous concept. That's not apples to apples comparison. There was no controls, nothing. And no one seems to be willing to do the conversions so they can compare the power. I mean, you take the Tesla Model X, which has 300-mile range, and then you're towing something and you reduce the range to 120 miles, and then you say, oh, well, electric drive's never going to work for EVs, for towing. And that's just ridiculous, because what you have to look at is the total amount of power. They were getting well over 40 miles per gallon still towing, and they didn't look at it that way. And they're towing it with a vehicle with a 3-gallon gas tank, essentially, if they had fuel in it, and they still got over 120 miles of range towing. And they're looking at the world the other way around. They got these glasses on and say, oh, this is no good, it'll never work. Well, it's not even a proper vehicle to be trying to do this with. And there's other things that can be done. It's all about the aerodynamics of the trailer and the aerodynamics of the trailer tow vehicle configuration. And that's never addressed in internal combustion engines hardly, because they have so much energy to waste. People don't care. But we got to get some new glasses on. We got to stop looking at the world through fossil fuel lenses. And we got to start looking at the world through electric vehicle glasses. And watt hours per mile and watt hours per horsepower hour, not this other stuff. We got to start throwing this gallons of gas out the window. That can't be our standard anymore. We got to move on. So that's why I'm shooting this video. And I'm going to let it go right here. I hope this helped a little bit. And we'll see you on down the road. Everybody take care. Thank you. Bye-bye.